With the SBA cloud native solutions and microservices in mind, our environment consists of services that are realized as service instances, which may be replicated across multiple network locations. A problem is, firstly, where to schedule the service traffic within these set of active service instances that can serve the request, or specifically finding the best service instance to serve the request at runtime. Secondly, scenarios with service transactions or a sequence of requests creating a state, we need affinity to a service instance. So after the initial scheduling decision, this instance affinity has to be maintained for subsequent requests of the service transaction. For this, we present our solution, Compute-Aware Distributed Scheduling, CARDS, which utilizes the compute capabilities of the available service instances of a service to select the best instance to schedule to, and it's able to maintain instance affinity for service transactions. The system is made up of geographically distributed sites with deployed service instances. As an example, those that can serve the request for foo.com/bar, the instances are marked in red. The client issues service requests containing a service identifier, and these requests are received by an ingress semantic router, which we will continue to refer to as SAR, Service Address Router. CARDS is performed in these ingress semantic routers as an on-path forwarding decision, unlike existing DNS-IP off-path solutions. Based on this decision, the request is forwarded to one of the relevant instances. Each semantic router performs this request scheduling on each individual service request received. In the case of service transactions, the first request is scheduled using CARD's scheduling approach, while for all the subsequent requests of the transaction, the client uses the IP locator from the response of the first request of the transaction to forward the requests directly to the same instance. The network of SARs form a 3.5 shim overlay to perform the routing on service addresses, or ROSA. The shim layer deployment allows to limit the routing tables to services supported by one ROSA overlay. As I mentioned, it is an on-path solution rather than the existing indirection-based solutions. It allows for routed or ingress-based traffic steering models, which CARDS proposes. It is decentralized and has no dependency on a central name discovery or address assignment system. And it's realized as a software router using eBPF-based forwarding over IPv6 extension headers for ROSA. The ROSA decision is the first level of the routing decision performed in a SAR. If a scheduling module exists, then CARDS is the second step of the routing decision. The key criteria which we had aimed for the CARDS algorithm to fulfill were, firstly, it has to be compute aware. So it does take the compute capabilities of the service instances into account for the scheduling decision. It should require little to no signaling overhead, which we were able to attain. It's only required at deployment. And thirdly, it should be and is implementable at link speed. So with the same system in mind from before, at deployment, each service instance is assigned a normalized compute unit, which is derived from the compute capabilities of the instance. So compute awareness of CARDS is performed by mapping of these compute units onto suitable routing constraints that can be taken as input during the ingress forwarding decision. To turn the compute unit assignments into routing constraints, they have to be flattened and joined into a compute vector for that specific service identifier that represents the set of instances. This is essentially the routing identifier interval. The interval is then distributed to all the SARs for this specific service identifier, which can then perform distributed scheduling as round robin over this interval for each request received. So for example, if SAR1 receives a request, it will send the first one to this service instance, the second and the third to this service instance, and so on and so forth until it reaches the end and then loops back to the beginning. Lastly, as I mentioned, it is implementable in P4 as well. Moving on to the demo setup, as I mentioned, it is an eBPF implementation. It consists of 3 servers, servers 1, 2, and 3, each hosting 1 or more service instances of the 3 services, A, B, and C. So for example, server 1 can serve requests of the service ID A and C, server 2 of B and C, and so on. We have 1 client generating requests, which specifies the service IDs A, B, or C. We have IPv6 routers, and we have SARs. Service A and B are routed, while service C is for the scheduled mode. To demonstrate the first behavior, we need to find an instance that can serve a request of service ID A. And since there is only one option, server 1, in this specific service instance, SI0, using ROSA, we don't need to specify the IP locator of server 1. Instead, specifying just service ID A is sufficient, and ROSA will route the service request to the relevant service instance on server 1. I will now demonstrate this. So I have already set up the demo using the Python scripts. And now we will move on to the screen of the client. To demonstrate sending a service request with service ID A, we will run a script which we refer to as send A. This just specifies sending packets, 20 packets per second with the service ID A. Now, if we go to server 1, we can see that the number of packets received per second has increased to 20. It's now receiving 20 packets per second. Whereas server 2 is not receiving anything. Likewise, server 3 is also not receiving anything. On the other hand, what if now we wanted to send a request with service ID B? There are 2 servers, servers 2 and 3, that can both serve requests of service ID B. So ROSA, in this case, will select one of the servers based on a routing decision. And in our case, it selects server 2 and this specific service instance. Showing that in the demo, when the client sends a request with service ID B, looking at server 1, it is no longer receiving anything. Server 2 is now receiving 20 packets per second. Server 3 is, as before, not receiving any packets as well. The service endpoint is selected based on the routing protocol, when the routing protocol populates the forward information base, which in turn is then used to populate the next hop information base. So for service ID B, at SAR1, we can see that the next hop is SAR2. So the request is routed to SAR2. At SAR2, we can see the next hop is SI2, which is on server 2. And so all requests addressed to service ID B are routed to SI2 on server 2. Previously, it was only in the routed mode. Now, when the traffic scheduling algorithm is added on top, cards only on SAR1, which is the ingress SAR, decides for each request which instance of which server to send each request to. Now, for service ID C, all 3 servers are hosting service instances that can serve this request. Unlike the previous behaviors where there was only 1 entry in the routing table, so all the requests for B were forwarded to SI2 on server 2. Now there are 3 entries. As I mentioned before, cards performs round robin over the available service instances that can serve the service request. There are 3 service instances that can serve requests of service ID C. So the first request is sent to SI1 on server 1, the second to SI3 on server 2, and the third to SI5 on server 3. The IPv6 routers execute the forwarding. Now to demonstrate the behavior of the traffic scheduling mode, we have a different script, schedule C, which specifies service requests with service ID C. Like before, if we go to server 1, we can see that it's receiving on an average 7 packets per second, 6.5. At server 2 now, it's also receiving 6.5 to 7 packets per second. Similarly, at server 3, we can also see that it's receiving 6.5 to 7 packets per second. This demonstrates the round robin pattern of cards. Previously, the compute capacities of 3 instances at the 3 servers were the default 1 compute unit each. So the requests are distributed equally across the 3 servers. What if now the compute capacities vary across the 3 instances and the 3 servers? So the newly assigned compute unit distribution is 1, 2, and 1. Service instance 3 on server 2 can now receive twice as many requests, and so is entered into the routing identifier interval twice, which is also reflected in the routing table shown here. Cards now essentially performs a weighted round robin over the service instances. So the first request received with service identifier C is routed to service instance 1 on server 1, the second to service instance 3 on server 2, the third also to service instance 3 on server 2, the fourth to service instance 5 on server 3, and then looped back to the beginning, again to service instance 1 on server 1. Now to demonstrate the case when we have a different distribution of the compute units, 1 to 1. I will call the script cards C. This specifies service ID C, but the compute unit distribution has been changed across servers 1, 2, and 3 from 1, 1, 1 to 1, 2, 1. And looking at server 1, we see it's now receiving about 6 packets per second. Server 2 is receiving double that, 10 packets per second. Server 3 is receiving 5 packets per second, similar to server 1. This shows that server 2 is receiving twice as many requests as servers 1 and 3, demonstrating the one-to-one compute unit distribution. The last behavior of instance affinity, only service requests are sent via the SARS-Rosa-Schindler. So for service transactions, the first service request is sent via the SAR routed path. All subsequent requests in the service transaction, which we refer to as affinity requests, follow the direct client service instance IPv6 path to the same service instance on the same server.